All right, last talk of this session, Do You Follow Me? A survey of recent approaches in dialogue state tracking by Leo Gatman, Lina Rojas Paraona, Benoit Favre.
Hi, so I'm Leo, and this is a survey I did with my supervisors. So this is not novel work, but I try to give you an overview of the recent advances in dialogue state tracking. So I think most of you are familiar with the modular architecture of task-oriented dialogue systems. Within this system, the dialogue states serves as a formal representation of the user's needs at a given turn. This is a central component because the system relies on this summary of the information to accomplish the task and decide which action to take next. Optionally, it can also query the database to get more information. The predicted action by the dialogue policy is then realized into natural language with the NLG module. And so traditionally, the natural language understanding module was to predict was to extract the semantic representation from the user utterance, and the information would then be aggregated and potentially updated by the DST module. This approach was to enable the DST module to account for the noise related to the NLU and potential ASR errors. And most modern approaches now actually combine both NLU and DST. And so a DST model takes as input the dialogue history to then predict the current dialogue state at a given turn. So here's an example of dialogue state tracking. The dialogue state typically takes the form of slot value pairs. These slots are predefined in an ontology, and the DST model has to predict the needed values to perform the task. And so here we have an example of a user who's looking for a room in a hotel, and accordingly the DST model retrieved these values. And I've chosen this example for the bottom part of this image. Here the user turns to booking a train, and this example highlights some of the challenges that may lay ahead. So the model should be able to resolve co-references. Here, there refers to the University Arms Hotel, and same day refers to Friday. And the model should also have some word knowledge to be able to infer that the University Arms Hotel is actually located in Cambridge, which would be the train destination. So here are some statistics about the most commonly used DST datasets. DSTC2 was introduced in the second dialogue state tracking challenge. It was one of the first DST public benchmark to evaluate different models. Then a few years later, MultiWOS was introduced, which was a multi-domain dataset, so collected in a wizard-of-Oz setup. So the dialogues are relatively more complex and can potentially cover multiple domains. And then 2 years later, there was the schema-guided dialogue dataset, which was based on specific schemas that could enable models to transfer to different unseen domains. This dataset was collected using machine-to-machine setup. So two machines would interact with each other to generate a dialogue template, which was then paraphrased by crowd workers. And so I've also mentioned some other less frequently used DST datasets, such as WAS 2.0 frames and M2M. Two common metrics are used to evaluate DST models. The main metric is joint goal accuracy. This metric consists in taking the proportion of turn where the predicted dialog state exactly matches the reference dialog state. And if we want to perform an individual evaluation of the slots, we can use the slot accuracy. And it's also possible to turn these accuracies into one single value using, for example, a macro averaged accuracy. Now, these two metrics can be somewhat difficult to interpret. Joint goal accuracy tends to be too penalizing because if an error is a single slot was mistakenly predicted at an early turn, then this error may be propagated through subsequent turns, and all subsequent dialog state will be considered as incorrect. And the slot accuracy tends to overestimate performance because in a given turn, most slots actually don't appear. And so there's two metrics that have been recently proposed to complement these metrics and address these issues. The relative slot accuracy ignores unmentioned slots and rewards a model for correct predictions, and the flexible goal accuracy is similar to joint goal accuracy, but more tolerant of errors that come from an earlier turn. So here I've illustrated some of the common approaches to dialog state tracking modeling. On the top, we have fixed ontology approaches. So a fixed ontology means that the model has access to a predefined set of values. And so we then need to train classifiers for each slot that are able to predict this distribution over the predefined values. Now, of course, this approach is inflexible because in a real world setting, unseen values are bound to come up. And so to address this, open vocabulary approaches have been proposed. We have extraction-based approaches, which try to extract the values directly from the dialog history. These typically work by predicting the span of the values. And we also have generation-based approaches, which use the encoder-decoder framework to encode the dialog history and generate the entire dialog state for a given turn. So in the past couple of years, there's been a lot of work in DST, and I'll try to give you an overview of the recent advances that have been accomplished. So far, the approaches that I've introduced do not account for the relationships between slots. However, slots are not conditionally independent. For example, the number of stars for a hotel might be correlated with the price range of this hotel. And so some have tried to explicitly consider these relationships. This has been done, for example, by taking a string of a sequence of slot names in the ontology and encoding this string through a transformer encoder to infer this relationship through the self-attention mechanism. It has also been done through graphs using graph encoders. We have an example here on the right, on the left, where domains and slots are represented as nodes. Another interesting advance is was enabled by large language models and consists in prompting these models to address unseen domains. So basically, a prompt is a string that conveys some information about the task you want to perform, and that is added to the input. and to condition the generation of the model. And here we have an example in blue of such a prompt in the context of DST. The information conveys the information conveyed about the ontology, and we have some description of slots in natural language, and the model based on this is able to address unseen slots during training. Next, this is also related to the previous advance, but as you all know, gathering resources and annotating data sets is quite complex and costly. And so some people have tried to leverage transfer learning to perform few-shot learning or zero-shot learning to mitigate this problem. And we have two main approaches. Cross-domain transfer consists in training a model on a set of domains and applying it to an unseen domain at test time. This approach, however, relies on the fact that the unseen domain at test time is similar to these other domains. And so to overcome this issue, cross-task transfer approaches have been proposed. The idea is to train or pre-train a model on a similar task, such as summarization or question answering, and then apply this model to the DST task. We have an example here on the right. So they trained a T5 model on multiple question answering datasets and then applied this model in a zero-shot manner to the DST task. The model was then able to perform the task by formulating questions around the slots that need to be retrieved. And one last advance I wanted to mention is, most of the work until recently actually was confined to English, but English is not the only language in the world. And so people have tried to go beyond English. Now, one way to do that would be to collect new data sets, but again, this is costly and difficult. And so an alternative is to use existing English data sets and adapt them to your target language. So some people have tried to use automatic translation and translate English resources, and then manually correct these translations. The problem with this approach is that your translations will not be localized, and so may be inadequate for the target language. And so others have used dialogue templates, such as those in a schema-guided dialogue dataset, and adapted them to the target language, and then had native speakers in the other language paraphrase these templates. We have an example here at the bottom where the translation is localized into the target language. So now these are all really exciting and interesting advances. However, there still are some major challenges before we can have competent task-oriented dialogue systems that we can use and deploy. And so there are many interesting research avenues, and I will articulate the needs around three axes: generalizability, robustness, and relevance. So the challenges we face when we deploy a system, a task-oriented dialogue system, is that there will be facing dynamic environments. These systems are used for a variety of tasks, for example, customer service or banking or technical assistance. So they may face diverse settings and domains. Again, the manual annotation of new corpora is difficult, and in practical settings might be infeasible. And an additional challenge is unseen entities that are bound to come up. So to address these issues, few-shot and zero-shot learning are definitely interesting, and I've touched upon this. However, the approaches we have so far still relatively low performing. The adaptation of existing resources is also quite a good path, and I've touched upon this as well. And an alternative would be to generate new resources, as we've seen in this keynote this morning. And the last path is continuous learning, where a model is expected to acquire new capabilities through time without forgetting about the previous ones. In the case of DST, this could be new domains. So this aspect is also related to the previous one. In a real-world setting, users may express themselves in different ways to mean the same thing, and we would want our systems to accommodate all these users. And several studies have pointed out that the performance drops when they're faced with realistic examples that deviate from the training set distribution. Another major challenge is long dialogues. I've talked about the problem of error propagation. These DST models struggle to actually correct the mistakes they might have done. And lastly, spoken dialogues. Of course, spoken language is quite different than written language, and comes with its problems. For example, ASR errors or speech phenomena such as disfluencies and repairs. Potential research avenues include data augmentation and regularization techniques to prevent overfitting. There's also been recently several evaluation benchmarks that propose to assess the model robustness when faced with different perturbations. For example, here, the model should be robust to paraphrases and also to a transcript that could come from an ASR model. And lastly, relevance. The existing benchmark datasets we use do not really reflect real-world conditions. They usually consist of a form to be filled in as slot value pairs. Then once the system is ready to query the database, it does so and outputs the results. However, a TOD system could face many different scenarios. And moreover, we evaluate DST models in a static manner. However, dialogues are dynamic, and if a DST model had made a wrong prediction, then the conversations would have deviated from its path. So some have proposed richer representations to encode more complex semantics, such as negations or compositions, with an associated corpus. The SM-CalFlow corpus is an example where the dialog state is encoded as a data flow graph that can be directly executed to query the database. Another example inspired by AMR is the dialog meaning representation, which provides a hierarchical representation of the meaning. Another aspect is the evaluation of the DST model. We usually assume that well-performing DST model can be integrated into the TOD system and will provide benefits, but this is not obvious, and there's been little work actually looking at the impact of the DST module on the system as a whole, and I hope to see more of this in the future. And lastly, instead of looking at one modality, there's been some recent corpora that were introduced to look at multimodal conversations. For example, SimC2, which provides conversations with VR rendered situations in a shopping setting. and also the multimodal dialog state tracking datasets, which is shown here. So in these two datasets, the conversation is grounded on an input video or images, and the DST model has to track visual objects in the form of slot value pairs. So yeah, thank you for your attention.
Time for a quick question.
Hello, it's Oliver Lemon from Heriot Watt. So just a quick comment really about the idea of using more real world conditions. Have you thought about using a task like multi-party dialog state tracking, where there might be, we're always thinking about one person talking to a machine, but in real world conditions, there's usually going to be more people in, maybe those two people talk to each other, one of them might be talking to the machine. So we've been starting to think about this idea of about multi-party dialog state tracking. I'm just wondering, is that something that you've already come across? Does that already exist? Or do you think it's a possibly interesting new direction?
Yeah, thanks for the question. I see where you're coming from, and I haven't seen any work on multi-party dialog state tracking, but definitely this is an interesting research potential track, and we in such a setting we would actually want to have such a DST module and be able to track what's talked about and have some kind of basis on which we can work on. So I hope we can see more work on this as well.
Thank you again.
Yeah, it's a topic right now, about 3 o'clock for remote.